Hello and welcome to IoT Builders, a live stream where we discuss a range of topics on the Internet of Things, starting from embedded devices to cloud services, all from the IoT Builder perspective. Today is 28th of June, and this is episode 34 of our weekly live stream. My name is Nenad. I'm a senior developer advocate for IoT at AWS. And in this episode, today, we will cover topics related to software-defined vehicles. And joining me today to discuss this topic is Francesco. Francesco is a principal solution architect for Auto coming from AWS. Hey, Francesco.
Hello, everyone.
How's it going? All good?
All good, all good.
Excellent. So maybe before we start into the interesting questions, you can introduce yourself so the audience knows, your background as well.
Absolutely. Thanks, Nenad, for inviting me in this episode. I'm Francesco Salamida. I'm Principal Solution Architect. I work in the automotive AWS team, and I have 30 years of experience, 20 of which I'm developing embedded systems, especially from the software point of view, not only. And in the last few years, been focusing on OEM and Tier 1 to help them to improve the software development process for in-vehicle.
Nice. Pretty cool. Excellent. So I think let's start with the easy question. So what are the current trends you see kind of shaping the automotive industry when it comes to software development? I think we had a couple of guests as well covering this topic, but I wanted to see from your perspective as well, like what you are observing.
Absolutely. I mean, software, as we all know, is everywhere, but what we see, the area where software is rapidly changing and evolving is surely the software that runs in vehicle. So the software that is powering the vehicles. And so we talk about software-defined vehicles once the software is actually the central piece that is helping to deliver the experience to the vehicle.
Excellent. Yeah. So I mean, what you're mentioning, the kind of this software-defined vehicle, maybe you can also give like an overview what actually that is.
Absolutely.
Since this is one of the trends that, I also talk with a bunch of your colleagues as well, and has been popping out like software-defined vehicles. But whenever I talk with people, they already have like a bit of different, definitions. So what would be your definition? Like how you see this?
Absolutely. I mean, every buzzword has when they happen, they means different things to different people. So it's good to have a good definition from our point of view. So I would bring up one slide to help me to describe what we mean for software-defined vehicle.
Excellent.
So software-defined is a way to re-architect the software so that the software, the functions that the software delivers, are more abstract from the hardware. Especially in the embedded world, there was always been a tight integration between the underlying hardware that is executing the software and the software itself. So that tight integration makes quite difficult to, let's say, abstract the software from the platform, as we normally do with other type of software. You think about the service. When you develop a piece of software on the service, you don't question too much yourself about what will be running that server. In the embedded world, it's completely different. You always have in mind what is your end platform. And this, of course, is allow you to fully utilize the platform, but at some point you are kind of linked to that platform. So the first step towards software-defined is to do this abstraction between the hardware and software. But also means also adopting technologies that comes from the cloud, like service-oriented architecture. The fact that you containerize this function in packages like containers, for example, and you provide mechanisms that allow you to update those even in pieces over the air to the vehicles.
Yeah, yes, this is pretty cool. I mean, I remember also talking with other people on this topic. Is like the experience of engineers who are kind of working on the embedded systems and so forth has been, not many people have that build up experience. But on the other side, you have people, the developers, who are quite familiar with high level languages and this containers technology. And now the question is like how they can leverage more or less those developers that have their unique ideas on what can be done, and have that kind of those developers develop applications that will be running on top of vehicle. But I mean, as of now, what you said is like this is kind of has been hard. But unless you have that kind of like hardware abstraction,
Yes.
which is not that easy compared to like just having it in a cloud. All the hardware is more or less like the same, and then you have the abstraction. You also would have kind of this interfaces to the screen, to like GPU, to telematics unit, to whatever not, right? So the idea here is to kind of have that abstraction, right? That's pretty cool.
That's correct. That's correct. Yes, and you
Yeah.
create this abstraction through layer of software and APIs, of course.
Yeah. But usually, like being in this bubble of being a developer, we don't tend to think about the actual manufacturers and consumers. We think of like how our development life gets easier. But maybe you can walk me out through this process. So like, first of all, how will our life be easier as a developer of building those services that goes into the car? But also like how what benefits the manufacturer has, and then what benefits the end customer,
Absolutely.
consumer has.
Yeah. In fact, yeah. Let's as you said, the session is about developers, but also we have to think what is the end goal, what's the promise that software-defined vehicle is bringing to different actors in the ecosystem. So
Excellent.
let's start from the customer. We are very customer obsessed
Yes.
at Amazon, and we want to start from there. So in terms of what this will bring to customers and customer in many ways, because also who is buying the car tomorrow will be probably renting the car or using the car in car sharing. So in this sense, the customer can be any of these guys. So the experience that these guys will have with software-defined vehicle is that the car will be changing over time, and is not just bug fixing that somehow they get to us, but also entirely new features that will be delivered over the course of the vehicle life cycle. And so not just at the beginning when you buy the car, of course, there will be a bunch of features, but also throughout the life of the vehicle, the 10 years, okay, maybe you can expect new feature, new service, completely new things that you never thought would be available on that car. From the OEM point of view, the fact that we will be able to collect more and more data from these cars will allow them to also think better to a new service and new business models, which today, let's say, of course, are based on common sense. But another thing is to actually create those based on the actual data that are collected to understand better how the customer are actually using the cars. And sometimes we see even OEM that are carry on with very old feature just for the fact that maybe if they remove, they will be disappointed. Even discovering that maybe with this data, that feature will never be used or be
Nobody
used very
uses it. Yeah.
badly
Yeah. That would be
by the
interesting. Yeah.
people. And last but not least, we are talking about developers. Software-defined vehicle are an excellent platform where to create innovation, and not like a boring platform. So it will probably even attract more talents to develop on this platform. But also software-defined vehicle means that also they will be able to cope with the complexity, and the complexity of these systems will increase more and more. So through software-defined vehicle, they can even better manage that complexity.
Yeah, this is interesting. It's interesting because I'm looking at this picture now, and thanks for kind of sharing this. And it kind of reminds me of what has happened with like introduction of this kind of modern phone that we have is like kind of the similar experience for the customers and as well as for the others. So yeah, it's quite interesting.
Absolutely. Yeah, that's the experience that they may get. Of course, somebody talk about vehicle being a smartphone on wheels. Even if that picture kind of deliver the message, but on the other side, I think a car still became very different from a smartphone in terms of requirement when it comes to
Of
functional
course.
safety and
Yes.
the fact that they hold our life when we drive with the car. So that's very important.
Yeah, this is excellent points that you mentioned. So, I mean, from the perspective of the phone, it's like, nothing bad will happen if it restarts or, there is some bug. But like, when you're sitting in a car and then the car is kind of getting updates or having some bugs, then it could be critical. Excellent. But that being said, like, how do you could you discuss this kind of challenges faced in the development and implementation? How do you cope with this kind of complexity? And how does this software defined vehicle infrastructure allows you to kind of cope with the complexity of course, from the developer perspective?
Yeah. Yeah, we have talked about let's say the software piece and how the software will evolve over time with software-defined vehicle, but we should not think that also the underlying platform will not change. Actually, will change dramatically, and I bring up here slides that show also how the software-defined vehicle will be a journey also for the underlying platform that will be running our cars. So we start from more a traditional architecture where you have all this, let's say, multitude of ECU or electronic control units. These are small embedded systems. They run on their own with their own embedded microcontroller or SoCs connected through some sort of buses such as CAN or Ethernet, and they exchange messages. But that is not sustainable to create a fully software-defined vehicles.
Yeah.
And so,
But what if you want to update like
exactly,
one functionality and then you
and
need to
the impact on the other. So yes,
yes.
exactly. So new architecture are being deployed already, like this domain architecture that you start to also see in today's production cars, where you go more centralized management of executing software that are let's say used by bigger domain-specific ECUs. And then the end goal is to get to like a zonal architecture where you are more and more concentrating the execution of the software on a bigger centralized HPC. Of course, HPC here should be intended for some of you that are familiar with the cloud, not with that kind of HPC, but still relative to the context of a vehicle. So still more powerful than today ECUs, but for sure less powerful because there are other requirements that, of course, needs to be considered, like the power and the heat dissipation and so on. So it still need to be limited somehow the power.
Yeah, I like this diagram, this zonal architecture, especially it kind of allows you to move all this complexity of like a traditional architecture into kind of those microservices, virtual machines, whatever is needed, and
Absolutely.
then have the actual actuators and sensors communicate via that kind of Ethernet. This is a time sensitive network.
Yes, that's the backbone of basically of the vehicle that
Yes.
connects all together. Yes.
Yeah, this is pretty cool. I really like this. But do you have kind of some examples of implementation of this? I remember we had Robert from ARM, and he was talking about this SOFI initiative as well. Yeah.
Let's maybe we can look at what AWS is doing for this software-defined vehicle and see how practically we are helping OEM and Tier 1 to
excellent, yeah,
to progress in the SDV. And I can summarize three, let's say, area where we can help OEM and Tier 1 to develop software-defined vehicle.
Oh, this is cool.
The first is to create this cloud-native approach that I briefly touched in the when I defined the software-defined vehicle. The second is to create virtual ECU, so to create environment in the cloud that could execute embedded software. And the third is about bringing along this target also all the tools that are needed to exercise this target, because of course the target itself needs inputs and needs to produce output in order to see if they work correctly. And by the way, Nenad, one thing that I want to underline, we are talking about vehicle here, but I'm sure in this audience there will be a lot of people that do not develop embedded software for vehicles. But I want to still highlight that all what we are saying can be easily applied to other domains where embedded software is being used.
Yeah, definitely.
As I will point out later.
Yeah, definitely. Yeah, this is a general approach. I mean, that we've seen across the industry now is like, even in terms of like IoT, which I mean, vehicle is more or less a thing that's kind of connected and extended, is that to kind of have that infrastructure, as you displayed earlier, that allows you to kind of start with the development and deployment of applications, and then have that communication back to the services that are in the cloud as well. So all of this, I think it's relevant as well. So yeah. Do you have some examples on like how this is bringing this cloud native technologies or whatever?
Yeah, cloud native technology. It's being recognized as a good foundation for next generation software defined vehicles. Nice. And as let's say as also a good example of the interest that the whole industry is putting in this approach. I can mention something called SOFI. SOFI is an industry initiative that has been created in October 2021, and AWS is a founding member of this initiative, and have seen an incredible growth in terms of participation and companies, from bunch of companies at the beginning, at more than 80 companies being part of this initiative. And what is this about? So is exactly that, the fact that you can bring this cloud native technology, create software stack that make it easy to leverage the cloud to develop in-vehicle software. And in fact, of course, you can try to, let's say, to virtualize existing stack, but still is not, you don't get the full-blown potential that you could get from a full cloud-native approach. That's what SOFI is bringing to the table. As an example of this approach, to make very practical, for example, we developed this example. What does it mean to have a cloud-native automotive software development? And this is an example where we have tried to develop a piece of software. In this case, was an example agent from a service called IoT Fleetwise, and see how that piece of software that is put in a container could be developed and tested in the cloud.
Nice.
On the left, okay. And of course, in the cloud, you don't have a real CAN bus, but so you have to connect a simulator. And how that same piece of software, without any modification, because we are executing the same binary on the actual car, thanks to something called AWS Graviton, which I will introduce quickly. You can basically, you don't need to change the binary. So what you test in the cloud, you just wire differently on the target, but ultimately you have the same thing. And of course, this give you the possibility to skip some of the tests, not all the tests on the physical target, but some of the tests can be skipped, and we call this movement shifting left. So shifting left means creating in the cloud the environment and creating the cloud, executing the cloud, the test, which can reduce what you do on the with the physical target. And everything that hits the physical world means higher cost. And so we want to not eliminate, because at the moment we are not at that stage yet, but even reducing substantially the use of physical hardware give you enormous advantage. And this is an example.
Excellent. I like this shift left. I remember it since the migration from like the on-premise to cloud and so forth. So yeah, it's kind of the similar thing now happening as well. So yeah, that's pretty good. So, but tell me about this kind of the process of actually. I remember, so I worked in the automotive industry and I was building like board support packages. I was working with the hypervisor, all that stuff. But like the first part is kind of getting that evaluation board, and then kind of, working with creating this board support package, putting the bits and pieces of the software that like other teams developed, testing this out and so forth. But like, how does that change nowadays? Since now technically you can just test all of those things in the cloud. Like how does that work? Can you maybe give?
Yeah, absolutely. At the bottom of the this virtual ECU is something called AWS Graviton, and you would ask yourself what is AWS Graviton?
Yes.
Why it's relevant? Okay, so first of all, the AWS Graviton is an architecture that has been introduced in 2018 as alternative to the x86. And actually, the initial intention was nothing to do with the embedded world. But the idea is that ARM is more efficient in terms of executing code, but also in terms of power consumption. So, and the idea is to provide an alternative platform to x86. But we, as embedded developers, have seen this a great opportunity to run our embedded code in the cloud natively without simulation, but directly on the same ARM architecture. And so they say don't with the performance never seen before, for example, from a simulator. In fact, the other alternative to execute embedded code in the cloud is through simulation. So it's a piece of software that is able to interpret the binary that would be, let's say, compiled for the target and execute. What's the problem with that? The problem is simply the speed. So the speed of a simulator compared to a native execution of code on Graviton, for example, with our benchmark, for example, we have seen QEMU simulator against native Graviton give you 70 times, not 70%, 70 times better performance. So this enable you to use it for many more use cases, even interactive development. But even testing, it's of course 100 times
Yes.
faster. So of course this lower the cost and accelerate the execution of test, which is fundamental for the velocity of the full process.
Yeah, I really love this. I mean, I think this is pretty great example. Like the Graviton was designed to kind of save money for our customers if they want to run some loads that are actually not related to automotive. But
Absolutely.
then another thing that was not anticipated is that this turned into being a great opportunity to kind of start developing applications for actually embedded systems and test them out without that interpretation part, which is great. Yeah, this is a great story. Yeah.
And as I was saying, that same approach can be used for any embedded device, because I mean it's well known that ARM targets are everywhere in the embedded world, in the IoT. So it's really a great opportunity to leverage this resource in AWS. And I will show you more later with how you can really start today to run your embedded code on AWS.
So you are telling me that all this Raspberry Pi cluster that I have here at home, I can replace with this? Is that
Absolutely. You can, yeah, maybe you don't want to replace for the runtime, because they connect with the same word, but for sure you can use them to develop code without having initially the target. But even when you have the target, you can carry on using that virtual target to do testing without connecting to the. So you can leave your, let's say, production code running undisturbed without having a second pair of Raspberry Pi to test your code. And only when you are happy with that development, then you can deploy with surely a lot more confidence that piece of software will actually run correctly on the.
That's true.
On the
that's amazing. That's amazing. Excellent. But usually you would have kind of like this CI/CD. But like with the embedded, I mean, I remember back in the days when we were creating like some preliminary CI/CD for our test framework. What we had is like we had to buy a specific boards, like NXP, iMix, whatever we were working on these days, and then have that cluster, and then like have that first type of development on them, and then testing, and then even though we did like a git push, it goes through the loop and so forth, it runs. And then it reports, and then we had like an actual car that kind of sits somewhere, and then we kind of deploy on that actual car. But like, how would the CI/CD pipeline look now when you are kind of working with this?
You well described what an embedded developer needs to go through initially when you start a new project. The first thing that usually you do. You go and buy an evaluation board. So in the area of software defined, that would change a bit. And for example, now I can mention ARM virtual hardware is an example of basically providing. You made the example of Raspberry Pi.
You
can have virtual Raspberry Pi available on the cloud
Nice.
through our virtual hardware. So instead to buy, and we all know that in the last couple of years, buying a Raspberry Pi has not been that easy and that cheap. And in this case, you can go on a web page, subscribe to this ARM virtual hardware, and have your Raspberry Pi instance up and running in seconds. And there you can start to deploy your Linux distribution, mock up your peripherals with some Python code. And of course, once that is done, which is more like interactive development, you can also, through the API, integrate that target into CI/CD pipeline and execute the tests every time you release a piece of code on your repository. So this is an excellent, let's say, opportunity to disconnect from the real one as much as you can. Of course, at some point you will need to get to the target. I keep repeating this, but it's very important message to not overpromise here. We are
Yes.
not replacing the hardware, we are complementing the hardware, and that's still, we believe, a huge value.
No, this is pretty cool. I really like this. I just like a bunch of ideas are coming in my head right now. Like, when it comes to this, this environmental parrot and all this, you can have some kind of like a virtualization layer
Yeah,
for like whatever you are developing. Because I remember back in the days I was working with different operating systems. So the idea is to have like 2 or 3 operating systems running on a single ECU with like
yeah,
Android for infotainment, some Linux for like rear view camera, whatever not, and AutoZar for like the CAN
yeah.
messaging and all that stuff, right? Um, but I'm just thinking now, like you can actually have all of those, in testing in like in the cloud without actually deploying this in the target, and then you can also have like um, the underlying piping between those and connections kind of simulation in order to enable them to communicate as they would in the car. So it
Absolutely.
you would definitely be able to test a bigger stack like of your applications, of course
Yeah.
not able to test some specifics that are related to hardware, but like a huge amount of software, and maybe go through that kind of software development, validation, testing, and certification phase.
Yeah, of course, once you have the single VECU somehow in the cloud, you can, of course, hook them together because, in a real application, it's very likely that multiple OS will be present in the
Yes.
vehicle. And also you want to move from a single VECU development to multiple ECU or multiple functions interactions. So
Yes.
one thing I want to mention here is that
Mhm.
when we talk about the so-called environmental parity and
Mhm.
how you create this artificial environment where you create when you want to execute software, it's important to understand that there is no the the virtual target. There will be even multiple virtual targets for a specific physical
I see.
target. So, and in fact, you need to let's say consider the trade-off between the fidelity of the virtual target and the effort that is needed to create that virtual
Oh,
target.
I see.
And
Got it.
so we have different parity level, and maybe I can share with you the different
Oh, nice.
parity level that you can have. And going from the left to the right, you can see the different use cases and how we address the use cases. But the point also to consider here in terms of parity, as you grow the parity level, then also you may expect lower performance. But
Mm.
so you want to move to start from low levels where you get the best performance, where you get, let's say, you start from the underlying virtual instance like a straight Graviton instance, and you start to create that abstraction at a different stack level. And you move on the right, which make, let's say, closer to the hardware, only when is needed, when the things that you are doing require that level of fidelity. And if you don't, it's better to be on the left, because left is less effort to bring up the target and probably better performance because it's all software. But once you have some use cases that require more interaction with the hardware, then you need to, let's say, deal with peripheral or the system at a lower level. And then you
Yeah.
go first with hybrid simulation, which basically
Mhm.
is the one that I showed with virtual hardware. A
Mhm.
second with the full simulation, which is still required when you don't have when your target is not ARM based. In that case, the only option that you have today is through full simulation. and that of course comes with a cost, and the cost is the performance that I was talking about earlier.
No, I like this kind of like starting small. I mean, if
Yeah.
this is kind of something that people are just introducing, kind of to start small, focus on the parts. This kind of environmental parity level one, like having your Android and QNX, because that's like a really high level thing that you can
Exactly.
work with, and then if the requirements increase, you can then increase the level of parity and like how you abstract things and so forth. So this is
adopting also new software stack like the Sophie allow to leverage the abstraction that those stacks provides to stay more on the lower level parity, and to stay away from the simulation somehow. So you break the monolith, you break the stack at higher level to the level required by your use case. And of course, having a software stack that allow that to happen, because some software stack are, as I said, really monolithic, provide you that flexibility, that performance that you deserve.
Yes. I'm wondering now if you have any like concrete examples of this. How this kind of like how would that look like? I mean, either like an architectural diagram or
Yeah.
yeah.
Yeah, absolutely. And maybe I can bring up one interesting use case from one of our customer, which has, let's say, brought that approach to in a real project. And
Nice.
so I'm talking about, for example, Marelli, that is a known tier one customer, and they were looking a way to create using the cloud, and specifically we a typical real-time OS that is used in many cars, many vehicles, is QNX. So QNX is now available on the AWS marketplace to run on Graviton instances. So you can use QNX to develop and test QNX workloads without, let's say, with the fidelity of running on QNX. And they have used this approach to do that. And so, for example, this is the architecture that they've put together, and which integrate a full workflow in AWS, starting from the development on the left, a CI/CD pipeline, and most important and most, let's say, if you wish, innovative part of this is about how the validation is done. So in this case, they could start with pure virtual validation. Again, going back to what I said earlier. So you need to understand to choose the right target for the right job. So probably unit testing in the virtual validation, then moving on to hybrid validation, where you are mixing up some virtual target to get with some physical target. And the last, you still have to deal with the physical world at some point in your development process. Still do full hill testing, but in this case, integrating in the main pipeline. So through that connection of their test bench with AWS Cloud, they would be it was possible to integrate also those stages into the main pipeline. So you have the full end-to-end pipeline sitting in one place, from virtual validation until the full hill validation.
Okay, so let me see if I can get it. So basically, they're using this kind of like Cloud9, which is like an IDE inside of the AWS console, and they're kind of developing those applications. I see here they're using like Amazon Code Whisper, which is kind of a hype right now to help them with the development process. That's pretty cool. and then they're having kind of this development integration environments on the EC2. So once
Yeah.
they are, let's say, ready with the code, they can just deploy directly to an Graviton instance.
Yes.
On top of
Running
Unix.
QNX, in something that is very close to the target, and then doing integration testing of that with other units, which maybe are physical in this case.
Nice.
And then finally end up with the full hill, which means hardware in the loop validation. Yes. And get the
So this will
results
kind
back.
of so this will produce those artifacts, and then
Yeah.
they're kind of go into this kind of validation process where you
Yeah.
said this kind of like hybrid validation, which consists of like physical targets as well as the EC2. Right. Okay. Got it.
Yeah,
That's
because
cool.
as we said, typically in the car, the embedded system does not live on its own. There is not
Yes.
one embedded system. There are
Yes.
many embedded systems that communicate in different ways, like Ethernet or protocols on top
Yes.
of Ethernet, like some IP. And of course, to do this integration, you need to have both units, either virtual or physical, in your test bench, so that you can create test cases that involve both.
This is pretty cool. I really like this.
Yeah, and I would say QNX has been a very important asset that we have introduced in our toolbox, and is providing a lot of value because it's the first real-time operating system available in AWS cloud from, let's say, very much widespread in the automotive.
Yes, of course. And so just this, the QNX. So there is an AMI that's already this Amazon,
machine.
Yeah, so it's already in the marketplace, so people can just take it and then.
Yes, absolutely. Yeah. And you pay with the pay as you go model. So you pay by the hour and
nice.
by the minute, and you bring up 1, 10, or 1,000 without worrying about the underlying resources, because that's up to us.
That's excellent.
So you can also parallelize the test execution. That's another important aspect.
Yes.
Because again, even when you have the target on your desk, usually you don't have hundreds of those.
Of course.
But you have few, and this usually limit the possibility to do testing, because of course you depends on the availability of that. And here in the cloud, you don't have to worry about that, because you can spin up, from your point of view, any number of instances. And when that test is finished, you just bring them down, and you stop also spending money on that.
Yeah, so basically, you can also stress test your backend as well. Like if you have, you can simulate having like 1,100, vehicles, or 10,000 vehicles, whatever, and then you can simulate they are kind of producing certain information, whatever, and kind of simulate how that will reflect for your backend services, if that's something that you would also like to test. Okay, this is pretty cool. I remember you mentioned you got some anecdotes from this specific projects. Maybe you can
absolutely
share this with.
Yes, I mean, I was talking with a customer that is, in addition to Marel, is adopting QNX AMI in their testing pipeline, and I mean they went in production recently, and for a period of time they were keeping the old test targets that were Linux based along the new one, and at some point one of the pipeline failed because of a bug found on the QNX. But that same bug was not showing up in the Linux. And so they, of course, they wanted to understand what was the difference, and so they end up going on the physical target on the hill
Yeah.
to understand what was which one was right, the Linux or the QNX. And actually, the QNX was right. So there was really a real issue. So that let's say by itself justified the fact that
Nice.
the QNX was providing value. That's because that bug could be detected before going physical, and anything that goes physical, the cost of fixing that bugs downstreams increase exponentially.
Yes.
And so more tests you do at the beginning, sooner you find out the bug, lower would be the cost of fixing those bugs. So this is a great example of how to leverage this virtual testing and virtual ECU to increase the quality and reduce the cost, and cope with the complexity of the software that is increasing ever and ever.
I mean, again, in the automotive industry, there are a lot of safety critical components.
Absolutely.
So even going through that certification process and verification process and all that stuff, if you can do this faster and have this a bit more automated, saves lives at the end of the day, right? So
Absolutely.
so
That's very good.
that is the priority number one. But second is like saving costs.
Absolutely.
And having this kind of speed of innovation, what you mentioned at the very beginning. So this is really cool. And, I like this kind of stories from the field that, people are actually doing this and reporting the benefits. So that's awesome. Okay, cool. I think, we are kind of running out of time. So anything you wanted to share that, we missed as of now?
Maybe I think we covered most, but I think that if we got you interested in this new way to develop and test embedded software, we can give you some good starting point, because we are builders. We like to also really show in practice how this concept can be put in practice, even from today, as long as you have an AWS account.
Nice.
Everything you have seen today is at your fingertips. You just need to go on the AWS account and start to deploy Graviton Target or follow our
Nice.
let's say details. So maybe I can bring two good asset on which we can share with the audience here, and maybe the first things that I could point to is a nice hands-on workshop, which basically explain how the environmental parity concept works. For a practical example, using the stack developed by Sophie, the reference implementation is called EWAL, and how you can develop a piece of software that could deploy in a Graviton, and that same piece of software could be deployed on a physical board, potentially on a virtual board like a Raspberry Pi, and it's a step by step. So as long as, again, you have an AWS account, you can follow the steps and get to the end and touch with your hands what are the different elements that bring that result.
So I mean, just from my personal interest, so what this does is like allows people to kind of, go through all the steps, but at the end, it will set up this kind of developer workspace where you can push changes to your code, and then there is a certain pipeline that will go and then deploy this to the what is it, T4G instance.
Yes, we'll build for ARM and deploy on a ARM target, and you can see, of course, that piece of software running and tested.
So this kind of builds out the Yocto based AMI with kind of this evil And then what is this kind of what I see Ubuntu, and then is this like
Yeah.
a container that runs then on top of this, or?
So the underlying operating system that we are using for both the physical and the virtual target is the SOFI reference implementation, which is called EWAL, which is a Yocto-based Linux distribution. And on top of that, we are running containers because EWAL advocate for using container and basically have a very thin user space, and
Yes.
everything that is supposed to be run in terms of application, and we are here talking about the application, is containerized.
Yeah,
So
makes sense.
everything that in this case is our demo application, which is an object detection with
This is
hardware,
okay.
is in a container running Ubuntu, then
Nice.
running on top of EWAL. In this workshop, we are not actually building the Yocto Linux image, but we have available on GitHub also the instruction how to build a Yocto Linux and create the AMI that we mentioned earlier, Amazon Machine Image, that could then be used to power up a virtual machine based on Graviton with that specific Yocto Linux. So Yocto Linux is of course used also across the board in the embedded world. So I think this will be also interesting in other contexts.
Excellent. Okay, cool. Can you go back? Just I'm interested in this just briefly before. I mean, hopefully people are. Yeah, I also shared the links as well in the comments, so you can grab those links. But here, so once. Okay, so this is only for building that container.
The container, exactly.
For the and kind of doing the inference, and then with this kind of YOLO v2 tiny. And then on the other side, you can use basically the same thing and then deploy it on different platforms such as Raspberry Pi. And
exactly.
Okay, got it. So this is pretty cool workshop. Yeah, excellent.
Yeah,
cool. And then the other example is the actual building of this AMI.
Yeah.
Okay.
In this workshop, basically, you assume that you already have an AMI available that is used to power the Graviton. In the other example, we actually show you how to practically create that AMI from sources. So you start from sources. Again, we are using the reference implementation from SOFI, but could be well reused for any other Yocto Linux distribution that you may have built for yourself.
Cool.
And until you get the AMI, the Amazon Machine Image, available in your account, that could then be used to power up your virtual target.
Excellent. Oh, this is wonderful. Cool. Okay, I think thanks a lot for showing all of this and then coming with all these images. It kind of really paints the picture of this kind of software-defined vehicles and what are the possibilities as of now. So I really appreciate this. Anything last you wanted to share with our audience since we are kind of coming to the end?
Yeah, I think that we are just at the start of this journey. There is a lot of things ahead of us, but I think we have already some concrete use case that we can address today to improve the software-defined vehicle journey.
Excellent, awesome. This is pretty cool. Yeah. And as I said, I really love this story and this topic in general. So hoping to have you coming back next time as well and kind of discussing further advancements. So
absolutely.
Let's see how that goes. Yeah, let's see how that goes. Excellent. Okay. I think then that's it for today's sessions. So Francesco, thanks a lot for taking your time to share your vast knowledge and expertise in this field and user stories from the from the field. So thanks a lot for that. And
you're welcome.
I hope the IoT Builder community also enjoyed this as much as we did actually discussing this. So Thanks a lot, everybody. And then, talk to you next Wednesday. Okay. Cheers.
Bye.
Bye.